So for today's Water Underground talk, I'm very happy to welcome Debra Perrone from the University of California, Santa Barbara. And what I want to start with is a question. And the question is, how did you first develop a passion for water, Debra?
That's a great question, Tom. I first developed a passion for water as an undergrad in a civil and environmental engineering program. I was part of this community-led project that worked on designing a water system. I grew up in a suburb right outside New York City, and this is a very developed area, lots of infrastructure, and I had never been to a community before that didn't have access to water, didn't have access to potable water at the household. And so this really inspired all the work that I've done in the past 10 to 15 years. This idea that people don't have access to water, this idea of water scarcity, and what can I do to inform the way that we solve these challenges, both at home, but also globally.
That's wonderful. I loved kind of going back to where you were growing up. How does your personality or personal interests make you a better water scientist?
I think that there's two components of my personality that make me a better scientist. The first is my curiosity. So this curiosity goes beyond my work in academics. I'm just a curious person. I ask a lot of questions. I love to learn more. And this has really helped me in academics because I ask a lot of scientific questions, and it's these questions that really get me excited. And the second aspect of my personality that I think really has prepared me for academics is my passion.
Mhm.
Ever since I learned about water, I've become quite passionate about it. I think it is the most important resource in the world. And I'm interested in sharing that perspective with students, colleagues, people more generally. And I'm really interested in talking about these stories of scarcity. So, talking about how ecosystems and livelihoods are affected by drought and overuse, how social injustices are affected by water access and water quality. I'm really interested in how I can use observational information, observational data to inform policy, to inform management, to incite change. And what's really motivating me is how do I use observational evidence, scientific evidence to mobilize change?
Wonderful. Yeah, I loved how you started alluding to mobilizing change and making difference in policy. Can you describe a little bit more of your work in California or across the U.S. and how that work is aiming to impact well beyond academia?
So there's two things in particular that I'd like to focus on. The first are what I'm calling research briefs, and these are 1 to 3 page summaries of the research that we do written for policy audiences. So what do these scientific findings mean? Why do they matter? Who cares? And how can they inform policy? The second thing is what we're calling research teasers. And these are 1 minute videos that really just get to the point and have really neat background visuals, neat music sometimes, and try to capture the imagination of both policymakers and lay audiences.
Oh, those are both really wonderful, and I look forward to seeing both of those. My last question is for the students and young professionals here. And I'm always interested to hear, what is the one paper, if you had to pick one paper of our massive literature, that has impacted you the most in your development, the one you kind of go back to the most in your work?
So I'm actually going to skirt around this question a bit. And the reason for that is because the thing that's actually been most inspirational to me are the newspaper articles by investigative reporters.
Hmm.
And those reports are what has inspired the work that I'm doing in California. This idea that people in California, so we're in one of the richest countries, if not the richest country in the world, in a state that by some accounts is one of the top 10 economies in the world. And yet there are people here that don't have access to potable water. They don't have access to water in their house. And to me, this gets back to my passion and this gets back to my curiosity. How do I do research that can help mobilize change? And these investigative reporters have really, you know, inspired me have really driven my curiosity. And so I just have to admit that it's more these newspaper articles than an academic paper in particular.
Oh, that's wonderful. Thank you, Deb.
Today, I'm going to share the story of an overlooked resource, how we can leverage hidden data to promote our understanding of the resource, and how overuse amplifies the water energy nexus. Today, I'm going to talk about groundwater. Groundwater is often referred to as an invisible resource because it's hidden beneath our feet. While groundwater may be stored under our feet, when it comes to the surface, it provides more than half of our global population with drinking water. Groundwater also provides more than 40% of the water used for irrigated agriculture globally. This map shows irrigated area serviced by groundwater. There are a few countries that really pop on this map: China, India, and the United States. And today I want to focus on the United States. There's no doubt that groundwater is an important resource in the United States. There's also no doubt that we are overusing groundwater in many places throughout the United States, which is leading to depletion. And groundwater depletion has a number of undesirable results. There are many undesirable results that have been documented widely, but there's one manifestation of groundwater depletion that has had little attention beyond the media. This is when groundwater wells run dry. When do groundwater wells run dry? Well, groundwater wells run dry when water levels decline so significantly that water can no longer be pumped to the surface. But until recently, it was hard to know where wells were vulnerable because groundwater well drilling is rarely studied. We didn't know where groundwater wells were constructed or the depths to which they were constructed. So we spent 5 years collecting, collating, and quality controlling groundwater well construction data for the United States. Here we show 11.8 million groundwater wells, which each one of these tiny gray dots marking one groundwater well that was constructed between 1950 and 2015. Well reports also reveal the depths to which wells are constructed, providing a lens into the subsurface. Light blue here indicates shallow wells, and dark blue indicates deep wells. We use this information about well depths to get an idea about where wells were running dry during the peak of the drought in the 2010s in the western 17 states. We found that 1 in 30 wells ran dry during the drought, and in some areas, as many as 1 in 5 groundwater wells ran dry. What can we do when the well runs dry? Well, one opportunity is to drill a deeper well. So we asked the question, are people drilling deeper wells over time? In addition to the information about the location and the depth of wells, groundwater well reports also provide temporal information about when groundwater wells were constructed. We can use this information to plot a time series of depth trends. Here's an example near Stockton, California. Across the x-axis, we have time. Across the y-axis, we have depth in meters below the land surface. Each one of these circles represents a groundwater well construction event. This highlighted well was constructed in the year 2000 at a depth of 100 meters below the land surface. If we analyze similar time series across the United States in areas with at least 100 wells, we find that drilling deeper is common in many areas across the United States. Here we show the rank correlations of time versus well depth between 2000 and 2015. Blue indicates that wells are being drilled shallower over time, and red and orange colors indicate that groundwater wells are being drilled deeper over time. What's the take-home message? Well, wells drilled more recently tend to be deeper than wells drilled decades ago throughout many areas in the United States. What's really unique about these data is that we are able to see these continental scale hotspots with locally relevant information. On the left-hand side, you're seeing a map of key aquifers where yellow and red indicates depletion since 1900. The map on the right shows our groundwater well data. We can use this local scale water data to inform the continental scale water challenge of groundwater depletion. To do this, we can pair drilling depth trends with water level trends to better understand the relationship between declining water levels and well depths. On the right-hand side, you can see a satellite image. The blue dot is monitoring well, and the yellow dots are constructed groundwater wells within a 5-kilometer buffer. Let's go back to Stockton, California. Here, the blue area shows the water level time series,
And over the period of interest, water levels are declining at a rate of 3 meters per decade. The yellow circles show the constructed groundwater wells within the 5-kilometer buffer of the monitoring well. And over the period of interest, groundwater wells were constructed deeper at a rate of 7 meters per decade. We can translate this information to a plot that can help us understand these trends at a regional level. Across the x-axis, we have well completion depth. Anything that plots on the left side indicates a shallowing trend. Anything that plots on the right side indicates a deepening trend. Across the y-axis, we have the water level trend. Anything that plots across the top indicates a rising water level. Anything that plots across the bottom indicates a declining water level. So for Stockton, the wells are getting deeper over time, so we would expect to be on the right side, and the water levels are declining, so we would expect it to be across the bottom 2 quadrants. And sure enough, for Stockton, we end up being in that overlapping quadrant on the lower right-hand side. If we zoom out, we can perform the same analyses for the entire northern Central Valley. On the left-hand side here, we see a zoomed out satellite image where the blue dots once again show the monitoring wells and the yellow circles show the corresponding buffers. In this region, the northern Central Valley, which is also known as the Sacramento Valley, we find that 83% of sites fall in that bottom right corner, where a site is a monitoring well with water levels recorded between 2000 and 2015, and its nearby groundwater wells constructed during that same period. Performing the analyses for the San Joaquin and Tulare Lake regions of the Central Valley, we find very similar trends. Our work in this region suggests that, for the most part, deeper drilling is not limited by the physical system, but instead by socioeconomics. Groundwater wells are expensive. We found that domestic wells can cost tens of thousands of dollars, agricultural wells can cost hundreds of thousands of dollars, and municipal wells can be more than $1 million. People don't have the money to drill the new wells, and that's the biggest problem. This is a quote from Jim Smith, who lost his well to declining water levels during California's most recent drought. These findings, declining water levels and deeper drilling, also have a number of implications for the water energy nexus. Coming back to our regional plots of the Central Valley, we're reminded of these stark results, but the trends that we see in California are distinct from the trends that we see in other places. If we move eastward to the High Plains Aquifer, the first thing that pops out is that there's a lot less clustering in that lower right quadrant like we saw throughout the Central Valley. The different colors here correspond to the portion of the aquifer underlying each state. While the northern and the central High Plains have very interesting trends, I want to draw your eyes to the southern High Plains. Here we see that most of the dots are spread across the bottom 2 quadrants, indicating declining groundwater levels, but also indicating that declining water levels are not always being met by deeper drilling. In the southern High Plains, we see that although monitoring wells indicate declining water levels, well depth trends are both shallowing and deepening. Upon a closer view of well logs and local groundwater management documents in the New Mexico portion of the High Plains, we found that our results are complemented with concerns about the future of water availability. Deep groundwater is of low quality and likely also of low quantity. Here, deep groundwater is brackish to saline, requiring treatment before most uses. Additionally, deeper drilling is not likely going to provide the yields that make it worthwhile, so managers are actually looking to import alternative water sources. Brackish water at depth is not unique to New Mexico. In a recent paper, we found that in several basins, fresh groundwater is less abundant than we previously thought. We found that fresh to brackish water transitions occur at relatively shallow depths of just a few hundred meters in some places. You can see this in the red areas mapped here. So is drilling deeper a solution or a stopgap to depletion? We suggest that drilling deeper is a short-term solution that amplifies the water energy nexus. But what do you think?
Great, thank you for those provocative questions and all the amazing research you tied through the narrative. Thanks for the Water Underground talk. And I look forward to exploring this research, and I'm sure all my students and students around the world will too.
Thanks so much, Tom. Thanks for inviting me to speak today.